Hi, my name is Wang Shan. I'm now doing the homework 10 of probability and stochastic processes. Now let's see the question 1. From lecture notes, collect definition and simple properties of examples of stochastic processes. Let's first see the Poisson processes. Poisson processes is defined by the following properties. The property 1, property 2, property 3, and this is the first order property mass of the Poisson processes. And the mean, which is the expected number, is lambda t, and the correlation of t1 and t2 is lambda to the square of 2 multiply t1 multiply t2 plus lambda multiply the minimum number of t1 and t2, and the covariance of the t1 and t2 is lambda multiply minimum number of t1 and t2, and the Poisson processes, the expected number of the Poisson processes is lambda t, which is a linear function of t. So it's like the longer we wait for a bus, and the longer we wait, the expected number of bus is larger. So this is Poisson process. And the second one is Poisson increment process, which is defined as yt equal to xt plus epsilon minus xt over epsilon, where xt is the Poisson processes, and this is the first order probability masses, and also the expected number of yt is lambda. The correlation of t1 t2 is this, and the auto covariance is this, and we can see the picture of auto correlation, and this area is lambda, which is not depend on epsilon. This is triangle with area which is independent of epsilon, and when the epsilon goes to 0, the triangle becomes an impulse with area of lambda. And the third one is point impulse processes, is defined as zt equal to dxt over dt, where xt is Poisson processes. And this is a picture of zt and the expected number. This is auto correlation and auto covariance, and this one is actually when epsilon goes to 0. And the fourth one is semi-random telegraph signal, and xt is defined based on Poisson points again. The number, and this the number n t1 t2 points ti in the interval t1 and t2 of length t, which equals to t2 minus t1, is a Poisson random variable with parameter lambda t, and this is the probability and also the xt. The first order probability mass is includes probability of xt equal to 1, and also the probability of xt equal to -1, and this is expected number of xt, the autocorrelation of T1 and T2, the autocovariance of T1 and T2. We can see that the auto correlation when when T1 and T2 is approaching infinity, and actually this auto relation is goes to 0. So when T1 and T2 is far away, and xt and xt1 and xt2 are less correlated. And the fifth is random telegraph signal, and this one is when yt equal to a multiply xt, and p probability of a equal to 1 equals to probability of a equals to -1 equal to 1/2. So this is a semi-random telegraph signal, and the first order probability mass is equal to half, and the expected number is 0. This is autocorrelation and autocovariance, and because the first order probability mass is equal to half, and we can say that yt might be a strict science stationary, because the expected number of yt equal to half, which is instant. And the sixth one is random walk, that we toss a fair coin n times and case the number of heads in the n tosses. So the first order of probability masses is this, and the expected number is 0, and this is autocorrelation. This is the autocovariance, and we know that when n goes to infinity, and this probably will be a Gaussian density. And the third one is Wiener processes, and we can see Wt equal to limitation, and t goes to 0, s to the power of 2 over t goes to alpha and goes to infinity. Xt, well, xt is a random walk. So this is expected number, and this is autocorrelation, and this is autocovariance, and this is the question 1 of the homework 10.